This is 12.5 part 2. A few more examples for us to do. Okay, so this one I'd like for us to find the term in the expansion of 4x cubed plus 3y squared to the 23rd that contains x to the 18th. Okay, so we know from the binomial theorem that n in this problem is 23, and they didn't tell me which term it was. Like if it were the 9th term, I'd know that r is 8, but they didn't tell me that. So for right now, r is unknown. The first part, 4x cubed, is going to be raised to the 23 minus r power. And the second thing, 3y squared, will be raised to the r power. And focusing in on the 4x cubed raised to the 23 minus r power, because we're looking for the power of x to be 18, that's why we're focusing on that part of the problem. That'll be some number, 4 to the 23 minus r, which I don't care what that is. But that will be x cubed to the 23 minus r. And since you have a power and a power, you multiply. So 3 times 23 minus r is 69 minus 3r. And that will be the eventual coefficient, exponent on x. And what we want that to become, that exponent, which is 69 minus 3r, we want that to become 18. Solve for r. So if we subtract 69 from both sides, you get negative 6. Well, if I could type in my calculator, I'd get the right answer. Negative 51. Almost said the wrong number. Then divide both sides by negative 3, and it should be 17. So the term we're looking for, now that we know what r is 23 choose 17, 4x cubed to the 23 minus 17 is 6, and 3y squared to the 17th. Okay, we're not out of the woods yet because we have to do all of our simplifications. 23 choose 17 is 100,947. 4 to the 6th is 4,096. X cubed to the 6th is x to the 18th, because 3 times 6 is 18. 3 to the 17th, wow, that's a long number. 129 million, I think, yeah, 140,000. 163. And then 2 times 17 makes the power y to the 34th. And then multiplying those three numbers together, the 100,000 number times the 4,000 number times the 129 million number, gives you a number that makes your calculator go to scientific notation because it's that big. So notice I wrote approximately. And when you're rounding this, I want you to make the first part of the scientific notation correct to 3 decimal places. So round to 5.340, 3 numbers after the decimal, times the power of 10, which would be 10 to the 16th. That's the coefficient. X to the 18th, y to the 34th. And that's how I want you to deal with numerical parts. If they get so big that they go to scientific notation, please write it in that form. And that came from, by the way, 5.339673 times 10 to the 16th. And so that's why I rounded it as I did. I had, again, 5.33967. So the 39 and 6, the 6 made it go up to 40 for the last 2 digits. All right. Now, one of the things that we can do with this is we can convert repeating decimal numbers into rational numbers, that is fractions, quite easily using what we just learned. So let's do this one. 0.1717171717. Okay. So if I expand that out, so take the repeating part off and write several iterations of that. And of course it continues in that pattern forever. That can be thought of as 0.17 plus 0.0017. And so let me show you where that's coming from. Okay, and what would the next one be? Plus 0.000017. That's this 17. And once we have 3 of them, I think that's probably enough. You could keep going if you wanted to, but I don't think you need to because you've established a pattern. Well, that's a series, and it's geometric. It's a geometric series. And we know that the first term of that series is 0.17. And if you can't just look at it and tell what r is, you can always take like the second one and divide it by the one right in front of it to find out what r is. That's 0.01. You might have known that because it moved the decimal place 2 to the left, it'd be times 0.01. Anyway, since the absolute value of this r gives us a number that's less than 1, this converges to the sum of the series, s, they call it s sub infinity, I'm not going to, equals a sub 1 over 1 minus r. So that's 0.17 over 0.99. And if you multiply that by 100 to move the decimal point 2 places over 100, that gives you 17 over 99. And that's the answer we're looking for, because rational numbers are defined to be any number that's writable as an integer divided by an integer. And of course the denominator integer can't be 0. But that's the form of a rational number. So that 0.17, which has a decimal in it, is not valid. You have to get rid of the decimal by multiplying by some power of 10 to move the decimal point a certain number of places away over to the right to turn it into an integer. Okay, let's do another one like that. 6.3215. Let me see what part of that I want to have repeat. Just the 215. Okay, 215 repeats. Now this time there's part of it that isn't repeating, so I'm going to pull that off all by itself. 6.3 plus, then it's going to be 0.0215 repeating. So if I write that repeating part out, a few versions of it, that's going to be 0.0 first 215 plus 0.0000215 plus ... So the part inside the parentheses is a geometric series with the first term equal to 0.0215 and r being equal to 0.001, because 0.000215 divided by 0.0215 is 0.001. And since the absolute value of r in this problem is less than 1, the series converges to s, which is a sub 1 over 1 minus r, so 0.0215 over 0.999, and we need to move the decimal for the numerator 4 places. So I need to multiply both top and bottom by 10,000. To move the decimal 4 places. And that becomes, let's see, 215 over 9990. Because when we move it forward to the right in the denominator, we have to add a 0 to go one more place. And then that's the sum of the geometric series. And so coming back to our problem, because we weren't actually done, that's 6.3, which is 63 tenths, plus 215 over 9,990. If you add those, you'll get 31,576 divided by 4,995 as your final answer. Okay, so let's do number 3. Did I number these? Yes, I did. Forgot if I'd done that. All right, let's do 0.9 repeating. course, that's 0.9 plus 0.09 plus 0.009, etc. That is geometric. The first term is 0.9. R is 0.1. So since the absolute value of R in this problem is less than 1, the series converges. It converges to S, which is the first term, 0.9, over 1 minus R, which is 0.1, which gives us 0.9 over 0.9, which is 1. So that means that 0.9 repeating is equal to 1. And you may think, well, wait a minute, if it's repeating 9s, isn't that not going to get to 1? Well, if you repeat forever, it actually is 1. If you stop before that, if you have a billion 9s after the decimal point, that's still not 1. But if you go forever and have an infinite number of 9s after that decimal point, it's actually exactly equal to 1. You may not believe that, so I have several proofs. Besides this is actually a very good proof. It's the geometric series proof way of proving that 0.9 repeating is 1. Let me show you a couple other proofs. Let's let x be defined as 0.9 repeating. And since we have an equation, that means that we're allowed to do stuff to both sides. So if I multiply both sides of this equation by 10, that's going to move the decimal one place. That'll be an infinite number of 9s. And if I take this equation, I can always subtract whatever I want from both sides. I want to subtract x from both sides. But on the right side, instead of subtracting x, I want to subtract something that's the same thing as x, which means I'm going to subtract 0.9 repeating from both sides. 10x minus x is 9x. 9.9 repeating, take away all the repeating 9s after the decimal, you're left with 9. So x is equal to 1, which you get from dividing both sides by 9. And x is also given to be 0.9. Therefore, 0.9 repeating has to be equal to 1. I can tell you're still not convinced. So let me do another one. This is a pattern recognition. You might need your calculator. 1/9 as a decimal is 0.1 repeating. 2/9 is 0.2 repeating. 3/9, which is 1/3, is 0.3 repeating. 4/9 is 0.4 repeating. 5/9 is 0.5 repeating. 6/9, which by the way reduces to 2/3, is 0.6 repeating. 7/9 is 0.7 repeating. 8/9 is 0.8 repeating. Following the pattern, 9/9 is 0.1 repeating. 0.9 repeating. And of course 9 divided by 9 is equal to 1. So therefore 0.9 repeating is equal to 1. You still don't seem convinced. Okay, well, I think you agreed that 1/3 is equal to 0.3 repeating. If you multiply both sides of that equation by 3, the left side becomes 1 and the right side becomes 0.9 repeating. Okay, I've got one more for you. This one's kind of cool too. 1/11, you might need your calculator to prove this to yourself, is 0.090909, so 0.9 repeating. 2/11 is 0.0909. 1 8, 1 8, 1 8, 1 8. So 1 8 repeating. 3/11 is 0.277. I'm sorry, 0.27272727. So 0.27 repeating. 4/11 is 0.36 repeating. 5/11 is 0.45 repeating. 6/11 is 0.54 repeating. 7/11 is 0.63 repeating. 8/11 is 0.72 repeating. Have you figured out the pattern, how I'm getting the repeating, the 2-digit repeating thing yet? You figured that out? Well, if I multiply the numerator over 11 by 9, like 9 times 5 is 45, that's why it's 0.45454545. So hopefully that's making sense to you. So 10/11, 10 times 9 is 90. So that's going to be 0.90909090, 90 repeating, if you will. And 11/11, 11 times 9 is 99. 0.99 repeating is the same thing as 0.9 repeating. And of course 11/11 is equal to 1. Therefore 0.9 repeating is equal to 1. Proven to you several times. So that's kind of a cool proof. I think it's interesting to come up with things like this that are out of your comfort zone, because in calculus we're going to have lots of things. We have add up an infinite number of things and it actually becomes exactly a number like 7/11. If we add up an infinite number of 636363s repeating, it actually equals 7/11. And so it's kind of an interesting phenomenon, and in calculus you'll explore that more. Okay, so that ends this lesson. I will see you in class.